Good evening all. Welcome to live session number 8 of Computational Fluid Dynamics for Incompressible Flows. I am Durga Prasad. So in this course, we started out with discussing different applications of computational fluid dynamics, and then we did a brief recap of the governing equations, the Navier-Stokes equations, continuity, and the energy equations, and different kinds of boundary conditions that we usually encounter with. And then we understood that all of these are formed under the class of PDEs, either elliptic, parabolic, or hyperbolic, depending on how information operates. We have completed different kinds of solvers and finite difference methods for elliptic, hyperbolic, parabolic equations. And last week we discussed how to analyze the stability of a given scheme. So this week we'll discuss about a particular formulation called vorticity stream function method, which is specifically applicable for a certain class of problems, which we will look into this particular week. So what are the main assumptions for this particular formulation, the governing equations, and how do we discretize those governing equations, and finally what are the different kinds of boundary conditions and how we apply them to this particular set of equations. And then I'll discuss some of the previous year problems, and then we'll actually do some coding for two examples that were discussed in class. One is the lid-driven cavity flow, and then the parallel plate channel flow. This we started out with saying that we have a 2D flow study, incompressible and Newtonian flow. Then the continuity equation is given by del u del x plus del v del y equal to 0, and the momentum equations are given as follows. So what we try to do now is again we are assuming it to be study, but let's say even if it is not study, we can still do with it. Let's say if it is not study, general case, even in that particular case, we can go ahead and do the derivation as follows. So the idea now is we have three variables here, u, v, and p. So three unknowns and three equations that we are trying to solve. And what we try to do now is a transformation where we define two new other variables, psi and omega, where psi is defined as a stream function given by u is del c del y and v is minus del c del x, and the vorticity function omega is given by del v del x minus del u del y. So what we try to do now is you can see the appearance of terms here. So you take the derivative of with respect to x for equation 3. The detailed derivation is covered in the lecture video, so I'm not going through the derivation. But the idea is you take a partial derivative of equation 3 with respect to x minus partial derivative of equation 2 with respect to y. And then we have to do some kind of algebra, and eventually you'll end up with these equations. This is in a general case, but for an unsteady flow, you'll have del omega del t also coming into picture. And there will be another equation which will attempt, like by definition we have taken u as psi y and v as minus psi x. So continuity is held by default. So ux plus vy is minus psi yx plus psi xy, because psi we are assuming to be continuous function. So both of them will be equal, and this is satisfied by default. So by assuming a stream function, we are satisfying continuity by default. So, and we have one more equation. This is one equation. The other equation is from this. You substitute v equals to minus del z del x and u equals to del z del y, then we'll have this equation del square psi del x square plus del square psi del y square equals to minus omega. So here again we have two equations and two unknowns. The two unknown variables are psi comma omega, which we'll be able to solve. So what we have done essentially is we have reduced our problem from a 3 variable one to a 2 variable one. So if we further restrict to a steady state flow, then even this term will actually go off. All we are left with is these two equations and two variables that we need to solve for. Before going to the boundary conditions, let's say you have some other terms in terms of energy equation also. Let's say you are solving natural convection problem or something, then you'll have additional terms here which are in terms of say Boussinesq approximation, where g is along negative y, let's say. Then you'll have one more term that is coming up here. The additional source terms. So when you do the derivative, these source terms will also get converted accordingly, and you'll have some additional terms into this original omega equation itself. So you'll have some source terms. I'll just denote this as S. So the general, if you want to write a general solver, so all we have is a vorticity transport equation. This is a vorticity transport equation. and then we have a Poisson equation that we need to solve for. So the different kinds of boundary conditions are very similar as what we have before. We have wall conditions where we have different kinds of walls. Let's say we have a stationary wall. So we'll have u equals to 0 and v equals to 0. So how do I define the variables that we are trying to solve for here are omega and psi. How do I get the values of omega and psi from these boundary conditions? Is again use the same derivation as before. U is 0. So psi y should be 0, which means psi is a function of x. And the other one, so what this means is essentially along a wall psi is constant. We don't know the value. It's an arbitrary constant. We will look this up, how this value changes for different kinds of problems. We will look up when we solve some problems. But the idea is we can just keep it some constant, an arbitrary constant. And then comes the other condition for omega, where omega is given by this expression. So how do I compute this value? So along a wall, we are saying that psi is constant. So if psi is constant along this direction, say this is my y direction and this is my x direction. So along y, psi is not changing. So we'll have psi y to be 0, and all we are left with is psi xx. So we have to use some kind of finite different approximation for this particular psi value. We can use a central difference scheme or something along the edges along. So if this is my node, this is my node 1, 2, 3, and so on. So you can get an approximate of psi. So first you have to solve for omega or psi. First, if you're solving this equation, you get the value of psi. Use that value here, or you solve for omega and then you have to get this value of psi x as approximation. Or you can also use Taylor series expansion. So for example, if we are solving for this particular point psi 1, I can write this as, let's say, write expansion around psi 2 is psi 1 minus, just to be clear, so psi 1 is at x equals to 0, psi 2 is at x equal to say delta x. So I'm trying to write an expansion around delta x, which is psi at 0 del square del x square times delta x square by 2. So you can use the Taylor expansion where this is basically my psi 2, psi at 0 is psi 1, del psi del x is by definition equals to v, which is 0, minus v, which is 0 in this particular, because it is a wall condition. We have this as 0, and del square psi del x square is minus omega, and this is evaluated at x equals to 0. So this is omega wall times delta x square by 2. So from this we can estimate the value of omega wall, or I can just write it as omega 1, which is at the wall, as minus 2 by delta x square times psi 2 minus psi 1. If the wall is moving, then you have a different velocity here, then accordingly everything will be changing. So for example, if the wall is moving, which we will solve later also, so let's say if this wall has a vertical velocity, so v is equals to some v naught, then all that will change is this del psi del x, instead of being 0, now it will be, this will change. So that will become, so psi x is minus v naught at the wall. We'll have minus v naught times delta x plus minus omega 1 times delta x square by 2. So from this we can get an equation for omega 1. So that is straightforward, but you have to do this for each and every point depending on the orientation, etc. This will keep changing. But the idea is straightforward. Do a Taylor series expansion around the neighboring point of the boundary, and once you do the expansion, substitute with the values of the first derivative with the velocity term and the second derivative with the corresponding omega, and then you will figure out the expression for wall, the boundary conditions for omega for walls. This is for walls. So similarly for say inlet or an outlet, let's say first we'll start with inlet. Inlet is just similar to whatever we have discussed just now. So let's say if I have an inlet with a constant velocity u naught, This is my x, this is my y. So first for psi, so we are saying v equal to 0 at the inlet. So u is given by psi y, which is u naught. So from this you can get psi as u naught y. This is some linear function, assuming the constant is some constant psi 1. And then we also have along the wall, along the inlet flow, v equals to 0. So psi x is 0. Now we need expression for omega. So we know the omega psi is a linear function with respect to y. So double derivative of psi will be equal to 0. So again, this is very similar to whatever we got before. So omega is minus psi xx, so which is same as this. So again, we need to substitute the corresponding value here, and we will get the equation for omega. So omega 1 will be same as whatever we got before this expression. I don't think there is any query in this. Similarly for outlet usually we assume that gradients are 0. So we have del u del x or any other gradient. In general, whenever we say outlet, we assume the gradients along the flow direction of that particular quantity, velocity or pressure, whatever we are talking about. Here we are talking about velocity is 0. So this is for outflow condition. So similarly for omega, this will be equals to 0, and even psi it will be 0. So these are the general boundary conditions for this kind of functions, but it gets clear as we solve more and more problems. So, but before that, are there any questions in this derivation or anything do we have to discuss? I kind of skipped the derivation, hoping that you have already gone through the lecture videos. I hope there are no questions in the derivation part, so we can go to some previous year problems. So for a 2D, so this we have just discussed. So for a 2D study, Newtonian incompressible flow, the equation for stream function. So the omega that we are talking about is del v del x minus del u del y. So in general, omega is a vector which has the x, y, z components. So this particular omega will be along the z direction out of the plane that we are considering about. Again, this particular formulation is only for 2D cases. So for a 2D case, this omega will be pointing towards outward normal of that particular plane that we are looking at. Extending this to 3D is little complicated. So the general assumptions about the flow in vorticity stream function, as I said, it has to be 2D. It has to be incompressible because we are using the equation del u del x plus del v del y equal to 0. As long as we are using this equation, it is an incompressible flow, and this equation is what enabled us to assume that u is psi y and v is minus x. When we kind of did this assumption, this equation is implicitly satisfied. So this is an incompressible flow. Newtonian, we have used the viscosity terms within the momentum equations are from this flow itself. Okay, now where the different boundary conditions. This is what you kind of have to get familiar is when you have to write your own code. Consider this problem where all are the walls except for the top surface, which is actually moving with a velocity u. So this is the standardly driven cavity problem. So at the top wall, if I have to discretize, what would be my bounding equation? Let's say I is along the x direction, and along this is the nth. At any ith coordinate and I comma nth coordinate, what would be the value of omega? The process is same as before. So we start with writing equations for omega, which is minus psi xx plus psi yy, and then we need to know the values of psi now. So along the wall, we have u is capital U, which is my psi y, v is 0, So this implies psi is not a function of x. So I can make this term equal to 0. So we have omega as only function of y. Sorry, omega is minus psi by y, and I need to determine this value. So as I said, for whenever we are near a wall, we start out with a Taylor series expansion around the neighboring point. So let's say this is my neighboring point, n minus 1. So I can write an equation for psi I n minus 1 as psi I n, the boundary point. We are we are going in the negative direction. So minus psi y delta y, where psi y is evaluated at the boundary point, plus delta y square by 2, and so on. So we know psi y is basically the velocity capital U, and this, because we are expanding it around the boundary point, all these values are calculated at the boundary value, at the boundary point only. We can directly substitute them, where psi y is minus omega of the wall, which is, this is again evaluated at the boundary point. This will be the corresponding I comma n. So we can just rearrange this equation. Psi I n minus 1 minus psi I n plus u delta y. I think this is one. So let me ask one more question here. This is with respect to the value of omega. So what is the value of psi I n that I should be using? Like here psi I n is also a boundary, right? So what would be the value of psi n that I should use? For any wall, we know psi is constant, but what should be the value that I should be using? Can I keep 0 everywhere? Okay, we'll get back to this question a little later again. Okay, let's take this problem. This is another benchmark problem. This is the backward step. So what would be the boundary condition for stream function and vorticity for the bottom wall, which is u equals to 0 and v equal to 0? We have again solved it just now. So for all the walls, all of them are walls except for this, which is an inlet condition. So for any wall, and this is an outflow, everything else is wall. So whenever we have wall, the condition is psi is constant, and omega will vary depending on whether it is a horizontal or which axis it aligns with. So if it is aligning for this particular wall, will omega be minus psi xx or minus psi yy? Or in general, I can write it as, or if you want to write it in general way, you can write it as del v del x minus del u del y. As we are going along this particular wall, only along the wall direction is what we are pretty sure that there is no velocity gradient. So the v equal to 0 is constant along the wall. So del v del x is going to be 0. But we cannot say anything about del u del y along the vertical direction we have some flow that is happening here. So this particular quantity is not equals to 0, but the first one, because v is 0 throughout the wall, this will be 0. So psi xx is 0 and we will be left out with just psi yy. So omega is minus psi yy and psi is constant. Yeah. Inside as in, okay, you are saying somewhere here. No, no, this is not I was just giving arrows to say it is an outflow condition. Okay. Maybe that was the confusion. It's just to say that there is an inlet and there is an outlet, because the others are walls, so it has to be differentiated somehow. Okay. This is again about writing the discretized stream function equation at a point 10, which is this particular point. If beta is delta y by delta x, this is more about writing the equation. These are the kind of questions you can expect in your exam if you are appearing for the exam. So the governing equation is we have del square psi. We'll just write it as omega is minus psi xx plus psi yy, where if you want to discretize this around a given point 10, omega 10 will be psi xx is you can use a second order stencil for this. This will be east point minus current one plus the west point by delta x square, plus similarly along the northeast, north, south and other directions. We have the north point plus the south point. Now all we have to do is just rearrange this equation so that beta comes into picture. So have delta y by delta x, so multiply with delta y square, and then you can just rewrite. So we have omega 10 times delta y square plus I'll take all the terms of psi on the other hand. So we have, if I multiply with delta y square, so I'll have a beta square term here, psi 11 plus psi 9. And here delta y will get cancelled, so I'll have psi 14 plus psi 6. And then on the RHS, we have 2 beta square plus 2. I'm just bringing that on LHS. This will give me psi 10. Can verify which of these options is. But this is a relatively straightforward one. All we have to make sure is what is the expression of beta that is asked in the problem. It can be either delta x by delta y or delta y by delta x. Accordingly, everything else will change. You have to just verify that question, which part they were asking. So if it was at a boundary, it would be changing accordingly. But as we will see later, when we are trying to solve this kind of equations, we will only solve for all the interior points using say Gauss seidel or something, and then we will enforce the boundary conditions. I'll explain in detail what I meant by that term when we actually see how to code this problem. Okay, which option is this? Which terms in the vorticity equation are responsible for the diffusion of vorticity where u and v are x comma y velocity components respectively and eta is the kinematic viscosity. So the viscosity terms are always the one that we saw in the governing equation is something of this form. We need a double derivative. This is something we discussed even in last week when we were discussing dissipation versus dispersion errors also. Whenever we have a second order derivative is what we call diffusion. Here we are saying diffusion of vorticity. So it should have a second order derivative with respect to this, and it should be multiplied with the corresponding viscosity. So it has to have eta. Because we are saying diffusion, it has to have a second derivative. Okay. So this is like a parallel plate channel flow. So where you have a uniform inlet velocity and the other side is an outflow condition. So which essentially means you are saying del u del x is 0. So for this particular problem, what would be the boundary condition for vorticity at the outlet? Okay, before going to vorticity, let me ask about what would be the value of psi first. This is wall, the bottom is a wall, top is also wall. So if both bottom and top are walls, psi is constant for sure, but what would be the values of psi? Can I make psi equals to 0 on top and bottom? So is this allowed? Can I take this same values on top and bottom? Like psi has to be constant. Should it have to be the same value or should it be different values, or what should we do about that? That is question number one. Now coming to the omega, we know for here that del u del x is 0 and u is psi y, v is minus psi x. On the outflow, we have del v del x also becoming 0. So this implies psi xx is 0. And we have omega as the Laplacian of the steam function, which will become something like this. Or you can also simply say, like as I said before, whenever we are staying in outflow condition, we are essentially imposing a zero gradient on that particular variable we are interested in. So we can simply say del x of this omega is 0, and from there we can, depending on which order derivative you are approximating this, you can just say the value of at the outlet is equals to the value of the neighboring point that we are trying to solve for. So if this point is, let's say we are calling m, this one is m minus 1. So the value of omega at m comma j will be equal to the value of omega at m minus 1 comma j. But let's say if you want to go in this particular fashion, how will I derive the value for expression for omega? This would be one way to simply say that the value of this boundary point should be equal to the value at the previous point. But let's say if you want to solve in this particular fashion, how would this pan out? So we have omega given by minus psi y y. How will I solve for omega? So from this we can write this as this with the first order approximation, and then we can write this, or we can add a ghost note here and then say from there that, sorry, omega of m plus 1 minus, and from there we'll get omega m minus 1, and we can substitute that back here. So this will be the second order accurate one. So if we use a second order accurate one, so we have omega m plus 1 is omega m minus 1, and from there we can estimate omega mj. But the point that I would like to highlight here is the complexity. So let's say if you were to go in this fashion, we have omega is minus psi by y, and psi by y will something along the y direction, but we know that for an outflow condition, it has to be along the x direction. So each and every time we have to evaluate the omega for that particular point, and then accordingly put that into our code. So the primitive variables that we are solving for, like say the velocity or the pressure, are directly available to us. We actually measure them and stuff, so we can keep them as the boundary conditions. But the moment when we kind of move into this stream function vorticity formulation, we have to evaluate these values of psi and omega at every boundary point, each depending on the problem, and then solve for the equations. That is possible sometimes, and sometimes it is not possible. So this formulation kind of has some restrictions in that way. Also, as I started out initially saying that this particular formulation when we are using, we are kind of assuming that it is a steady flow. But in general, if you have seen the derivation, we do not actually use that thing anywhere. So during the derivation, all we are trying to do is we are taking a partial derivative with respect to x for this and subtracting the partial derivative of y of this equation. In that derivation, there is nothing that is stopping us from adding these terms here, del u del t and del v del t. So if you have added those terms, you would end up actually getting in terms of omega, the equation in terms of omega directly like this. So there is nothing that is stopping us from this, but in order to solve this equation, we would still require to know the value of omega at t equal to 0, which itself is an unknown to us. The problem is usually known in terms of primitive variables alone. So if it is a steady state problem, if you know that the problem has a steady solution, then we can neglect this term and we can go ahead and solve this particular problem. But otherwise, so it's very difficult to get the values of omega for even the boundary conditions or initial conditions anywhere, because omega is something that we eventually do in the post processing for most of the problems. Okay, move on to the next problem. I think that part is clear. In vorticity stream function method, the wall can be considered as a streamline. So streamline is where you have stream function as constant. The contour of stream function is basically the streamline. So whenever psi is constant, we call that a streamline. And for a wall, we have this particular to be satisfied always, as long as the wall is the no slip condition is satisfied. So this is true. Yeah. In vorticity stream function method, the wall can be considered as a streamline with value. Okay. If I have considered that as a streamline, what will be the value of psi? So this is something that we have to look for. So it can be any value as long as it is a constant, it should be fine. Actually, this is like all options are correct. Yeah, this is the last problem. Which terms in the vorticity equation are responsible for convective transport of vorticity? So as I said, diffusion has a second derivative, while the convection is only the first derivative terms. So it's basically the advection equation. So you have u del omega del x and v del omega del y. These are pretty straightforward ones. Now let's solve some problems. So the ones that are discussed in the lecture are where one is a lid driven cavity flow, where you have all these as walls, stationary walls. And then you have the top is also a wall, like an impermeable one, but with a fixed velocity. Impermeable, so we have the vertical velocity to be 0. This is my x, this is my y. So the governing equations are straightforward. So let me just go to the code part. You can see how to implement this. If my screen is visible. Ignore this parts for now. Let's start from here. So the first step is discretization. So this is the domain that I'm considering. So we will discretize this uniformly across x and y directions. So say this is my length L. This is my height h. So dx is basically L divided by nx minus 1 and dy is h by ny minus 1. Beta I'm defining as dx by dy by dx, whatever it is. So I've written equations assuming beta is dx by dy. And then this grid params is something that is, you can think of this like a dictionary that stores all these values. So you can look the dictionary back here, which will have all these values nx, ny, dx, dy, beta. So later I can use this directly. So once we have the grid, then we will, yeah. So the first step is making the grid. Then we have to define the flow parameters. The flow parameters are let's see the governing equations. So I'm using the non-dimensional form of this governing equation. So in the non-dimensional form, we will have two equations. One is omega. This is the non-dimensional omega. This is the Poisson equation. I will refer to as Poisson. And then we have the momentum equation, which is converted into, just write it as u omega x plus v omega y. Instead of mu, in the non-dimensional form, we will have 1 by Reynolds number times the Laplacian of omega, where u is psi y, v is minus psi x. So the parameter that we are, and u is, when this is non-dimensionalized, we will have u star, which is basically 1, and everywhere else v star is 0. So this would be my boundary conditions in the non-dimensional form. So this is the one that I will be solving for. So these are my governing equations and the boundary conditions. So the flow parameters is the Reynolds number, and then we will discuss what is R and this a little later. So now comes the boundary conditions. So we have boundary conditions for omega and psi. So as I said, all of them are walls. So psi is constant. I am taking psi is 0 on all the walls. And for omega, we have two different kinds. One is if wall moving with the velocity, and everywhere else these are the stationary walls. So we have derived this equation just a while ago. So all you have to do is, let's say I'll do for one again. So let's say if you're doing for the moving wall on the top. So you take the neighboring point. So this is say some ith point, comma n minus 1. And this will be I comma n. So I'll write the equation for psi neighboring point, psi I n minus 1 as psi I n minus psi y calculated at I comma n calculated at I comma n times delta y square. So this will be psi y is basically my velocity, in this case 1 plus so from this I can get the value of omega I comma n. This is for the top wall, and for the other walls u will actually be 0, so you'll have only two terms. You do not have any additional delta y term that will be coming into the picture. So that these are the conditions. Omega 1 is basically the first one. So for the left wall, we have this minus 2 by delta x square times psi 2 minus psi 1, and whenever we have this column, it means along the entire direction. Similarly, for the other end, for the right wall, we have minus 2 by delta x. This instead of 2 and 1, it will be reversed. And top and bottom is also similar to the left and right walls. Those are stationary walls. Only for the top wall, when we have a velocity, we'll have this extra dy term that is coming in. For psi, all of them are zeros. So these are the boundary conditions. Similarly, for velocity, I can keep the boundary conditions. Everywhere it is 0 except for the top wall, and same v for the vertical velocity, everywhere it is 0 on the walls. Then we call this function called solve. So what are the equations that we are trying to solve is, we have two equations. So the process that I'm going to do is, first I'll assume you have to initialize something. So you have to assume some values of omega comma psi, and then what we will do is, with the assumed value of psi, I'll solve for omega, which is this equation. So since the psi value is assumed, I can calculate u and v from this, where psi y I can use a second order approximation for this, and psi x I can use. Again, this is how do I do this? So for suppose if you are using u, if I say psi y, so the ideal way is this, something like this. So what is this method called? Yeah, it is central difference, but this particular portion is very similar to whatever we solved in the last week, last week for hyperbolic equations. So we discussed different methods with respect to this thing, as in kind of when you have upwind scheme, or we discussed several methods. Which one of them is this? Or maybe I will rephrase the question. So if I want to use an upwind scheme, how would this change? Let's write it as ULJ. So as we discussed last time, whenever we are dealing with the hyperbolic equations, then we need to make sure that we use information only that is available with us. We should not use anything that will be there in a future time or in a space that is beyond where the information is already propagated. So, but here we are essentially using information from j plus 1 and j minus 1. So depending on the direction of the flow, this may or may not be consistent. If here in this particular problem, I consider a very low Reynolds number, around 50 or something. So this wouldn't actually give any problem, even if I use this one. But if the Reynolds number is higher, then information would actually have different speeds. Then you might have to use a different scheme. So for example, if u is along this direction, say u is along the positive direction, or since we are dealing with j along psi y, so let's say u is along this direction. So then using j plus 1 minus, I should use a scheme where I'll use only the previous value. So something like I have to write my, let's say I'll only write along one direction. So uj should be written in terms of j, j minus 1. So since we are dealing with the second order scheme, so something like this. This is a second order, so equivalent second order should have something like this. Then whatever we discussed before, you can draw the Taylor's table and then get the expressions for A, B, C, and then use that equation accordingly. That will be second order one. Otherwise, you can simply use a general first order scheme where uj is basically written as psi j minus 1 by delta y. Again, this is assuming that u is along the positive y direction. If u is along the negative y direction, then this would replace. And we discussed how to kind of do this automatically by using that modulus last week itself. So I don't want to go into all of that. For now, we'll restrict to very low Reynolds number. So we can simply use this equation. So this is basically called central differencing. So with central differencing, we can go ahead. So I'll get this u. Similarly, I can write an equation for v, substitute them back in this equation. Again, omega is omega y is what I'll use, the same kind of central differencing for omega x omega y. And for all of these equations, then I'll get the discretized equations, which I'll plug in back and solve them. So that is something that is independent of problem. So as we move from problem to problem, the only things that will be changing are the boundary conditions. The governing equations and the way we are discretizing is constant. So I've clubbed all of them in one file, which is solver. So which takes this term separately. So let's say this is the vorticity stencil. I'm calling this stencil, that whatever one we are using now. So alpha is your u term, which is psi ij plus 1 minus psi aj minus 1 times we have this other coefficients coming into picture. Like if I do the rearrangement here, so here I'll have, for this I'll have a 2 delta y. Similarly for omega, if I use a central difference, I'll have another 2 delta y, and I have a Reynolds number. So I'll have some 4 term, and then I'll have a beta coming into picture where beta is delta x by delta y. If I do the rearrangement, then this is the equation I'm getting. The derivation is already discussed in the lecture videos, so I'm not going through that again. If you have any queries, you can ask me, but it is standard. The detailed derivation is there in the lecture videos. So this is the equation taken from there directly. Similarly for v, this will be psi I plus 1 minus psi I minus 1 times, instead of multiplication, we'll have a division operator. Now we have different terms, clubbing all of them together, we have our final expression. So what this function does is it takes in given values of grid and flow parameters, which is the Reynolds number and beta values, and then returns the value of this equation, which is basically from this one set discretized. I'm writing this as omega ij is some function of all other omegas. So what I will be getting is a new value of omega ij that will be used later within the Gauss-Seidel process. So in the Gauss-Seidel, this goes into the Gauss-Seidel where it will take this stencil that will give me a Gauss-Seidel update, and then we will use the relaxation that we discussed before, where this is the old value plus whatever is the Gauss-Seidel update that we are getting. So this we are doing just to kind of get some stability, but you can explore different values, what omega to use, etc. That is kind of trial and error that we have to do, changes from problem to problem. So now we have two different kinds of stencils. So stencil is something that returns the Gauss-Seidel update value. So here we have two equations. One is this vorticity transport equation, which we will solve in the first step. Then we'll get a value of omega and use that to find the value of corresponding psi. That will be the second equation. So this is the Poisson equation. So for that, the stencil is again straightforward. So we have psi I plus 1j, psi I minus 1j plus beta square times psi ij plus 1 plus psi j minus 1. Plus we have this omega term coming to picture. This is kind of the source term that we have, the constant term in the Poisson equation, divided by 2 into 1 plus beta square. So this is also taken directly from the slides. So this also goes into the same thing. So there is an additional equation. These two equations we are already familiar with. So this we have already solved. So what we are doing is for I equals to 2 to nx minus 1, so which means we are solving only for the interior points. So these are my interior points. I'm solving only across the interior points first. But then I'm doing it multiple times, where sweep basically is done to ensure that previously up until now whatever equations we have solved, for example when we solve the energy equation, it is just one equation. You solve the energy equation and directly get the temperature. The velocity values are given to you directly. However, in this problem what is happening is we are solving two simultaneous equations and these are coupled to each other. So the omega that you are going to get, this u and v are again a function of psi, and this psi is a function of omega. So when you kind of solve them simultaneously using Gauss-Seidel method, you're only solving one equation at a time. So first I'll solve omega equation. So the method is as follows. So first I'll solve the omega equation and then use that omega solution to solve for the psi equation, get a psi solution and solve for omega equation and then proceed further. But the problem that happens, which we will see later, is the method that we are using, the solver that we are using is going to influence how whether the solution converge or not. So if for suppose the error in the error when you solve the psi equation is very high, then that will actually propagate into omega much faster than the other way around. This is some specific problem pertaining to Gauss-Seidel method alone. There are tricks to solve this, which we will not discuss here. If time permits, we will discuss towards end of the class and not discuss end of the sessions. It's not covered in the syllabus of this particular course. So, but the problem, one way to tackle that is you just don't solve it once, but then you keep multiple sweeps. Where sweep means, so you do not solve it once, so you get this update multiple times. So you take the omega equation, you get some solution, then instead of directly sending it to omega psi equation, you again solve the equation, same equation again multiple times, and then eventually you will get some solution. So you pass this here, and this solution will then be fed into the psi equation. And similarly for psi, you will again do the same thing. So you'll do multiple iterations and eventually the solution will go into this omega equation. How many sweeps to do, and that is something that will change. We do not know beforehand itself. It depends on the constant that we are having here. So that changes this. But the problem is how ideally what is already known to us is for this particular formulation, this equation is more any errors in this equation will actually propagate much faster to omega, and then it will cause that will kind of divert the solution. So what we will do is we will use more sweeps for Poisson equation compared to omega equation. So in other words, we will update omega equation for every one update in omega equation. We will do say 10 or 20 updates for the stream function equation. So that is what the sweep function will sweep variable will do here. And then we have some other terms. Velocity, this is some helper function. What it does is just calculates the velocity from this. So u is basically psi ij plus 1 minus psi ij minus 1, and v is there will be a minus here, I plus 1 I minus 1. So I've just taken it inside. So psi I minus 1 j minus psi I plus 1 j divided by 2 delta x. And then pressure terms we will see last little later. Now the solution. So initially we are assuming psi omega everything to be 0 throughout. And then this is the main iteration loop. First we'll copy them into an array, but this is only to ensure that we can calculate the error later and see how the error is applying as a function of iteration number. First step is apply the boundary conditions. So this apply BC is a function that will change from problem to problem. So for the lid driven cavity, the apply BC function is the cavity BC, which is this particular one that we have already discussed. If it is a different problem, then this will keep changing. So this is something that changes from problem to problem. And then all we have to do is the one that I told before. So first we will solve for omega equation and then use the omega solution and solve for psi, where here we'll use the different number of sweeps. So for this one I've used 1, and for every 1 iteration in omega, this is going around 20 iterations for the stream function equation. And then we'll calculate the relative residual, so psi minus psi old by the previous value. And then we'll keep a tolerance for it. If it is less than, I've used 10 power minus 6 or 10 power minus 5, and then we'll get the solution. Once you have the solution, then we can compute the velocity, pressure, whatever is required from there, impose the velocity boundary conditions on them, and then return the results. And then some post processing where you kind of plot all these things. You plot the convergence or contours for heat, contours for UV, and vorticity streamlines, all this. So we'll leave the post processing for now. So this is the solver function. All we have to do is call this, and then we'll do some plotting. I'm not running this now, or maybe I can run it. I think. You can see how the error is reducing. This is with the Poisson sweeps of around 20. I'll get the solution and all. But let's say if I reduce this to say 1. So for every 1 sweep of omega equation, I'm doing 1 sweep for Poisson equation also. Then let us see what happens. So it kind of converts for this particular problem. But yeah, this is something for this particular problem, but it is not guaranteed always. So usually what happens, maybe I'll show you another problem where this becomes actual problem. Yeah, but I think the solver is clear. So if the solver is clear, maybe I can expect you to write equations for the next one, which is parallel plate channel flow. So this is the problem. Let's say uniform inlet, where U is U, V is 0. This is, let's put outflow condition. So this is my length L. This is the channel with let's say H. These are walls, no slip. The governing equations remain the same. There is nothing to worry about. The only problem is the geometry is also very similar to that one, except that L and H will be different here. Instead of 1, the ratio will be different. But the code remains the same. The only thing is we need to give proper boundary conditions, boundary values. So first start with psi boundary values. So what will be the value of psi on left? We can start with C1 equals to 0, and that gives me psi is u times y. Again, let's say we'll solve the non-dimensional equation only, and we don't have to worry about this thing. So let's put u equals to 1. Only deal with the non-dimensional forms. That will simplify the thing. So psi is linear at the inlet. Let's say psi equals to y. So At the outlet, we'll see little later. We don't have to worry about the outlet. So what about the top and bottom walls? Psi x has to be 0 and psi y has to be 0. So we know psi is at this particular boundary, we have psi equals to 0. Let's say I'll take psi equals to some constant C2 and let's say I'll take it as 0. Now when I do the same thing on the top wall also, I'll get the same equation, psi equal to C3. But the problem is we need the psi to be constant throughout this length, and also I do not want any singularity at this particular point. We need psi to be a continuous function. So at this corner, if I kept psi top to be 0, then the problem that happens is at this particular corner, I'll have from this equation it will be equals to h. But from the other equation, it becomes 0. So that kinds of gives some similarities which we want to avoid. So what we will do is we'll keep the same value throughout. So such that psi top, instead of keeping 0, like it has to be some constant, so we'll keep that equal to h. So on the top surface we'll have psi equal to h. On the bottom surface we'll have psi equals to 0. So this is so that in a way satisfies both equations. So on the top we have psi is a constant, so that will be h. So del psi del x along this direction will be 0, and along y we will see later that comes from the solution anyways. So we need to only worry about this one. And then for the right boundary is an outflow condition. So we leave the outflow as this. So similarly for omega, the same as before. Omega is straightforward. Inlet and walls we have already solved for it. So all you have to do, as I said, is take the neighboring point, write a Taylor series around the neighboring point, and then substitute for the corresponding values of u, and then get an equation for omega. It will either be minus ix or minus psi y depending on which wall you are looking at. So if it is here, it will be minus ixx, but if it is on the top and bottom walls, it will be minus psi y. So you have to expand accordingly and then get an equation for omega. So let's say if I were to do it along the inlet, it will be minus ixx. So I have to take this point. We will psi1j. Sorry, I'm expanding along x. So this will be psi x. So from this I can write equation for omega. Psi x is minus v. Here v is 0, so I don't have anything there. Similarly for all the other boundaries you can write. The only difference from the previous problem is how we implement the value of psi here. That would be the only difference. So instead of keeping 0 everywhere, because we have an inlet condition here that and it has to satisfy the kind of continuity without giving any similarities, we need to enforce the different constant value on the top and bottom. This was not a problem in the previous case because everywhere it was 0. So everything remains the same except for these boundary conditions. So as I said, this is along the bottom wall and top wall, bottom and top walls are straightforward. And at the inlet, this turned out to be 0 for me. You can check this also. Otherwise, you can also write it in the one fashion that I shown here. You can write it like this also. Then we have psi given a linear function. What this collect does is it just creates an array from 0 to n minus 1 and then multiplies it with here. Then we have, and next this is the outflow condition. Outflow, I'm just doing that whatever is on the outside should be equal to this one. So whatever is on the end point should be equal to whatever is at n minus 1 point. So this is for the outflow condition. At y equals to 1, this is the bottom wall, psi is 0, and the top wall we are keeping psi equal to h, as I told just now. Velocity conditions are same as before, and then we use the solver. So solver is the same as before one. So the only thing that we need to see here is with respect to the Poisson sweeps that I want to show. So for 20 sweeps, this is a kind of profile. So here is the developing region, and then you have the fully developed flow. So let's say if I reduce this Poisson sweeps to 1, you can see this is kind of becoming unstable. So it is kind of a problem for some solutions. So there are some tricks to solve this. So people have already studied this. What is the problem with this thing? There are something called fast Poisson solvers, which actually does this in pretty other ways. You also do some kind of Fourier transform, and then you can do it, or you can use some multi-grid solvers also. Why they work? People who are interested can look into them, or if time permits, we will do that also at some point of time. Okay. This is kind of I think even with 10 sweeps, it wouldn't actually work. Just give it a try. Even with 10 sweeps, it is actually a problem. So I needed at least 20 sweeps to actually solve it. And then we already learned some other tricks also when we were discussing about Gauss-Seidel method. So one is this relaxation, where either you reduce it, or we also learned about the over and under relaxation. So the problem here is if the values of errors in psi is actually very low, they'll actually blow up the values in omega. So what I have done is we will use we need to speed up the solution in psi, because errors here are actually propagating into omega. So in order to speed up this, we'll use a over relaxation for psi, and in omega we know that it is becoming unstable, so we have to do something called under relaxation. So that is what I have implemented here. If you see the solution in FP is the flow problem. So this R is my under relaxation factor, and this omega S4 is the over relaxation factor. So the implementation is both of them are same. So essentially there is no difference in the implementation. So if you see the solver, we have 1 minus omega relax times omega this thing. So what we are saying is if you are using a value greater than 1, you are giving more weightage to the new update than the older one. So this means you are kind of accelerating the convergence of the solution. And when you are under relaxing it, so whichever means whenever your omega is less than 1, then what we are doing there is reducing the value of weightage for this Gauss-Seidel update, and in a way kind of slowing down the convergence. So that is kind of will kind of give some kind of stability to the problem. So you can test it out. Let's say I used around 0.9, which is kind of way too high. Let's say I reduce it to 0.3 or something, and then I'll reduce my Poisson sweeps. You can see previously this kind of didn't give me a solution, but now you can see how it kind of converts to the solution. So you have to play around with these values and then determine the optimal value for your case. For Poisson solvers and for particular kind of solutions, it is already kind of, there are some optimized values of what the value of omega and what the value of relaxation factor has to be and all. But in general, for a general problem, if you are using only Gauss-Seidel method, then you have to tweak with these values, the relaxation and over relaxation and under relaxation. I think I have the convergence plot also. You can see the convergence plot. Yeah. So this is with when I have used 10 sweeps and 0.3. So let's say if I use 0.5, can't do this. Okay. I can't actually change this now. Yeah. But I think the idea is clear. So if for suppose you are not getting a convergence, the tricks that we do is either you kind of do an under relaxation, or you go and do some more sweeps of the Poisson solver that will kind of ensure a solution. Again, all of these are valid only up to a given limit. So this is again for a Reynolds number of around 100 or something. So if I keep a very high value of Reynolds number, then this might not just work. So what would be the reason that it will not work? Per se, I give a Reynolds number here of say turbulent. So this is a channel flow, so it's around 2000 or something. So let's say I give around 1000 or something, and let's say it didn't converge. Then what could be the reason? So it will not converge. So what could be the reason for this now? So I can use either a very low relaxation and get some solution, or what other things can I do? So these are the two things that we will do. Any other suggestions that we can do here, like within the same formulation? Like we can always go to other formulations, but within what is the testing function formulation, what other things can we try? So there is one more problem in the solver, that that is with respect to the way we are creating the stencil. So this is a stencil that I was referring to. So where we have, these are my U and V written as alpha and gamma. So this is basically psi del y multiplied with the Reynolds number and so on. So when we have a very high Reynolds number, and depending on your grid size accordingly you have to choose. So this particular value of alpha, if this is greater than 1, if it so happens that in your particular problem, if alpha turns out to be greater than 1, then T1 becomes negative for the same values of omega. And then that would give some other results, like that would give some non-physical results. It can also lead to divergence. We will see why exactly we need this to be less than 1 and other stuff also. When we discuss Scarborough criterion, then it will be more clearer. But for now, the idea is we need to make sure that all these coefficients are positive. If these turn out to be negative, then they kind of give us some kind of divergence in the results. So one way is use this solvers only for Reynolds number. The other way, this problem is essentially coming because we are using a central difference scheme. So when we discuss about the stability for any forward space schemes, as I was saying here, so whenever we are referring to any forward space schemes, we will kind of end up with the same problem again. So then we have to switch to an upwind scheme. So this is one difference that you will see people who are already familiar with finite volume method will understand this much easily. So here in finite difference, you can see it is very kind of little more clumsy in a way that if I want to use a higher order method, all I have to do is just write this Taylor table and then derive an expression for that and implement that particular scheme. But doing the same thing in finite volume is actually a little trickier. Once we go into finite volume, that will be better clear. And I think someone was asking this question, why we are still learning about FDM when we can actually use finite volume method. So when you want to implement a higher order scheme, this is kind of somewhat easier in finite difference compared to finite volume method. Here, all you have to do is write your corresponding extension and But again, there are other challenges with respect to the mesh. One thing that all the examples that we are referring up until now are like some rectangular things that we are using. So here we are assuming that the mesh is also kind of can be done in some simple ways. But when we have a complicated geometry, then either you have to come up with some functional form where you can map this space in, for example, if instead of solving this problem, let's say I have this problem. Instead of a parallel plate channel, let's say I'm trying to solve for uh, an annular flow. and I'm solving inside this one. So here again, you can convert into cylindrical coordinates and then assume axis symmetric and then convert it into a single variable problem and solve it, but maybe I'll make it a little more complicated. Let's say you have a different geometry, the one common one, let's say the aerofoil one, not a very good aerofoil, but let's say you have some complicated geometry where you cannot simply put grid points. Then all you have to do is you have to find some kind of a mapping where your original x comma y will be converted into some alpha comma beta and or some other coordinates, and in these coordinates you will do the finite difference in t. So accordingly you have to transform all your governing equations into this space and then use whatever scheme you are using, whatever we discussed just now, and then we can solve this. So trick like this have already been used. One thing that you might be familiar with is when you solve boundary layer equations, we use a similar kind of transformation and then we can solve it using finite difference methods. So, but the main challenge is this with respect to geometry. As the geometry becomes complicated, finding the right transformation will become difficult. And once you know the right transformation, doing everything else is straightforward. But the advantage with this method, finite difference, is we can kind of do any level of order of accuracy that we need. So all we need to do is create this stencil accordingly, and that is kind of straightforward by now. Just create a Taylor table and then solve the set of matrix equations, and that will give you these coefficients. All you have to do is take care near the boundaries, and then you'll have your kind of high fidelity finite difference code that can give you any arbitrary level of accuracy. Solving the equations is a different problem. So I think that person who asked the question is not present right now. I don't know if he's there, but I think that answers that question. Yeah, so these are the problems I have for this week. So to summarize, we started with vorticity stream function formulation. I didn't derive that though, but the equations are straightforward. The major assumptions are it has to be 2D flow, and yeah, so it has to be a 2D flow. Study is essentially because from an implementation point of view, if it is unsteady, then knowing the value initial condition is quite tricky. So we restrict ourselves to steady flows, and then comes the incompressible, where we use this del u del x plus del v del y equal to 0. Newtonian flow, where accordingly comes the momentum equations. So all we do here is we transform this a 3-variable problem into a 2-variable problem. So instead of solving 3 equations, we will be solving the 2 equations. So now comes the there might be some problems where okay, there is some one zero also here. You might be solving a problem where you need to find the value of p. For suppose, so let's say we solve the channel flow problem. So after solving the channel flow problem here, we got some solution, some velocity profile. Let's say I want to find the pressure inside this channel. So how do we do that? All we need to do is take this equation. We know u in terms of psi. So we know u in terms of psi. Once we solve the psi and omega, you know u comma v. You can substitute them back into this equation and this equation. So all you have to do is solve second equation plus del del y of third equation will give you an equation entirely in terms of psi. All we need to do, this will essentially be some kind of Poisson equation in pressure, which is a function of this psi. Psi is already known to us from the solution. We already solved everything, so we'll know this value. So this is again another Poisson equation that we need to solve. Once we solve this, then we'll get the value of p, which we can use. So that is the second part I was referring to. The other one that is left in the code is where you have the source term. The source term is the one, this f of psi that I was referring to, which is basically, this is my u times ux uy vx vi. Source term is ux times vy minus uy times vx. These are the derivatives accordingly, second central difference fields. Once I have the pressure source term, the pressure stencil is again, this is just like the Poisson equation stencil. You have pi plus 1j, I minus 1j, beta square I j plus 1, j minus 1. And then what? Previously it was omega here for the stream function equation. Here this will be the source term that I am adding, divided by 2 into 1 plus beta square. And then recover pressure is where you take the source term and then solve the Gauss-Seidel equation for that. That will give you the pressure. So this is straightforward one. Like once this part is clear, I think the other part is straightforward. So we can get, so by solving only for two equations, we are directly getting the third equation. So what we are implicitly assuming here is this particular flow is incompressible, and by that assumption, we are by using this psi x and psi y, we are able to satisfy this equation by default. So this is kind of implicitly satisfied. That is kind of reducing one equation to us and kind of simplifying the problem. But the challenge is now we need to know the boundary conditions in terms of psi and omega, which is not possible always, because the primitive variables that we usually measure are velocities and pressures. So transforming them is what we discussed next for different kinds of boundary conditions. For walls and inlet and outflow conditions, we are derived, but there are other boundary conditions also. There might be problems where you might have to you might have to specify pressure. So let's say you want to solve a problem where there's something like this. Let's say this is some channel. So these are two walls. This is your domain, and let's say this is open to atmosphere. And this is also open to atmosphere. So you want to solve some problem like this. So what I meant to open to atmosphere is the pressure here is atmospheric pressure. So if I want to solve this problem, then it is not in any of the boundary conditions that is solved. It is actually a Dirichlet boundary condition for the pressure term. But in the vorticity steam function formulation, I do not have any pressure equation. So I cannot directly impose the Dirichlet boundary condition into the pressure. So now if I have to give this condition, then I have to solve the pressure Poisson equation. So I have to solve for this del square P equals to this C, and I have to estimate this psi from there, which means I'm actually solving the original problem again. So here, if I'm specifying this P, like I'm solving for psi in terms of P, so which is more difficult than compared to solving the original. Like I can directly solve in terms of UVP using other techniques, which is much better than solving this equation for every boundary condition. Each time I solve an iteration, I have to solve this and update my boundary condition, which is more difficult than this one. So this formulation, though it is useful in some scenarios, it cannot kind of come in a very generalized way compared to other methods that we will discuss in next week and coming weeks also, where which can be generalized to much more problems. But this is simple for some problems. The another problem that is kind of well studied is, let's say you have a differentially heated cavity, and let's say this is adiabatic. So this is another problem where again we can use this particular formulation. So all that changes is in the governing equation. We'll have additional term coming because of the temperature differences. So that will be the G beta T minus T naught that I was referring to before. This also can be solved using vorticity steam function formulation. And again, this is restricted to certain cases, like as the Reynolds number, or in this particular case, Grashof number increases beyond a particular point. This again is not applicable because the problem itself changes then. We discussed these problems. I think these are straightforward. Are there any questions? Yeah, I think if there are no questions, these are the things I have from my end. And yeah, thank you for joining. If you do have any questions, you can also feel free to comment on the, like all these sessions are recorded and will be uploaded on YouTube. You can, there's a comment on YouTube channel also, or you can also post them on the discussion forum where the instructor will also be able to respond on them. Thank you for joining, and we'll meet next week, same time.